All right, I guess we can start. So hi everyone, thank you for coming. I know it's difficult. It's the last presentation in the mobile track. My name is Guy Fiegel, and what I'm going to review with you today, and what I'll try to present today is how we in Vonage, and in particular in Vonage Mobile, trying to enhance our voice over IP quality for our mobile product using AWS services, and what are the challenges that we are facing and how we thought to come up with some of the solutions to that. So if you are not familiar with Vonage, Vonage is a voice over IP telecom company. We are using, our entire infrastructure is based on voice over IP, focusing on the US market. And for the last 2 years, we came up with Vonage mobile application. We actually have a couple of mobile applications, but our primary goal is for Vonage mobile application, which allows you to make phone calls between two devices for free, basically, if you have the Vonage mobile application installed on your smartphone. And we also offer cheap international cost structure if you want to call into someone that doesn't have the Vonage mobile application. We also give the ability for free text messages between the users. We have the application for iPhone and Android, and we have a lot more features to come in the next releases. And what I want to show you right now is a really short movie that just describes the app. So then, we can all have a common language about the product and how we actually use AWS in order to enhancing the product quality. So let's do that.
This is Mike. Mike's feeling smart. Why? Because he just downloaded the new Vonage mobile app on his smartphone. And that's the smartest way for Mike to keep in touch with friends and family all over the world. With the Vonage mobile app, Mike can make free high-definition calls and send free texts to anyone who has Vonage mobile, anywhere in the world. Calling his parents in Mexico? Free. Texting an old college roommate in Spain? Free. And the more people Mike gets to download the Vonage mobile app, the more people he can call or text for free worldwide. Vonage Mobile makes keeping in touch with friends around the world super easy for Mike. In fact, unlike Skype, which forces him to create a new Skype address book, with Vonage Mobile, Mike's existing contact list is right there in the app. He can see who else has the app, invite those who don't, even see how much it costs to call a friend who doesn't have the app yet. Because even if his friends don't have Vonage Mobile, Mike can still talk to them for an average 30% less per minute than he can with Skype, and 70% less per minute than if he used his regular mobile plan. Mike can add calling credits through iTunes or Android Market right from the app. And what's really smart is Vonage Mobile doesn't require unique user IDs. Mike's phone number is all his friends need to know to see who's calling or texting. Smart, right? So now because of one smart app downloaded to his smartphone, Mike can stay way more connected to anyone, anywhere, for way less money. So now you know why Mike's feeling so smart. Vonage. Sounds good.
All right. So as you saw, our user base, millions of users so far, are globally located. So we have users all over the world. As you saw, we are giving free service for some of the phone calls. So we need to keep our cost structure low enough, but on the same time to give high quality of service. And that's why we really are facing some challenges in doing that. What I want to present here is actually you can see on the left side is the internet and cloud services, and we're going to talk a lot more about that side. That's the basic infrastructure of Vonage. So you can see the entry point for the mobile clients is the internet coming all the way, hitting Access SBC for security and control. Then we have a bunch of different proxy groups different voice over IP proxy servers that can route the call. We have in the middle, you can see smart routing engines to support different routing to different carriers and interconnecting with the carriers. And then on the right side is also some kind of a cloud, but it is the PSTN cloud. And what it means is basically it is the cloud that we as a telecommunication company interconnect with our partners and other telecommunication companies over circuit switch connections, over VoIP connections, and some other connections. So we have the far right end that really is the core of how can we terminate the phone calls all over the world. We are using dedicated gateways to do that. What means is that we actually need the physical location of the gateways. So for instance, we cannot put the right side on AWS because we need the physical interconnectivity to our partners. So that's kind of a burden on the entire infrastructure. What we can do is see what is the infrastructure that we can enhance quality on the right side, on the internet, on the left side, which is the internet cloud part, and in particular, our media relay servers, which are the servers that carry the voice over IP packets from one side to the other side. So that's the main architecture. From software architecture, we have three main software components. Telephony side, we are heavily C++ based. We have our proprietary C proxies. We have our billing and rating engines, and we have our real-time call state managers. And real-time call state managers are actually built in order for us to know in real time for each of the users how many calls they are up and running. We can prevent fraud by doing that, and we can route the call based on the status of how many calls they have. On the application side, it is all REST APIs. It's all based on Java. We implemented our own Vonage push service in order to communicate with Apple Push and with Google messaging service. And if you think about it, because we are running on mobile applications, the mobile application is not always on the foreground and it's not always running, but we still need a way to reach those users to connect the call, to ring. And that's the reason why we need to implement push services. So we have that as part of our application APIs and infrastructure. The last part is our messaging infrastructure, which is, again, REST APIs. It's all Java-based. And what I want to point here is that we are using Redis, which is a NoSQL data structure to store the messages. And we are using Redis with persistency, so it's a little bit different. Many companies are using Redis for cache only. We are doing the saves after every transactions, so we do have persistency with Redis, and I'm going to talk a little bit more about Redis and what we are doing with that. And we actually didn't deploy Redis in AWS, but there are some things that we are doing that are related to messaging APIs. So what are the challenges in voice over IP networks, and in particular with mobile clients that are globally located all around the world? I think there are a couple of challenges, or the main challenges that we saw. The first one is related to latency. And basically, it's what's going on the wire between the mobile device and the network, different carriers around the world, different networks. It can be 3G, it can be 4G, it can be Wi-Fi connections. And we don't have control over that, right? So, and because voice over IP protocols and RTP in particular is really sensitive for delays and low bandwidth and even traffic blocking, then it's really hard to control what is going on those users' end. And we need to take care of that with some kind of sophisticated algorithms to basically know what is going on and try to give the best routing to those packets. And we're going to see that later on. I talked about global users, and with global users and multiple clients all around the world, there's always this question about, should I go peer-to-peer between the two clients, or should I go into a centralized place using relays and maybe by doing that, solving some of the challenges that we saw. Now, by doing peer-to-peer, I mean implementing a direct connection between one mobile client to the other mobile client, so they can actually transfer the RTP protocol packets between those two clients. So if you think about it, then only the signaling goes into a centralized place, but the packets themselves and the voice over IP traffic is being transferred between the clients. So if you have two clients on the same physical area or the same country, then obviously the call quality will be much higher than traveling all the way to the US, for instance, and then go back. And that's as opposed to tromboning. What is tromboning? Tromboning is, and we call it tromboning because it's basically the traffic is doing like a shape of trombone. So it's going all the way from one location to the other and back to the first location or to a different location. And not always you can avoid tromboning. So I talked before about terminating into PSTN, that far right end cloud that you saw. And if you want to terminate into a PSTN network, then obviously you cannot do a peer-to-peer to that network. So what it means is that traffic needs to go all the way from your mobile client to your centralized location, which you have this termination point, and then maybe the call is actually going to be terminated on the same country that it was originated from. So then from call perspective, it will go all the way from one site to the other and back to the first site. So not always you can avoid tromboning. Intelligent routing is one of the things that we are working really, really hard to make sure that we enhancing and the call routing based on the call need. From the messages point of view, obviously two main challenges. First is performance. So when one user is sending another user message, we want it to be reliable. We want it to be really fast. We want two sides to actually send and receiving the message as quickly as possible. So that's performance. Again, if I have customers all around the world, I need to take care of that. The second one is storage. In our mobile application, we let our users to attach pictures, to attach music files, to share their geolocation, and many other rich content. So at the end, we need to store it somewhere. We need to persist that file. We need to be able to get it back into the other client whenever they need. And that's actually challenging because that's a lot of storage that you need to manage. And that's a lot of storage that you need to back up in some cases. And again, remember that this is a free service, so we need to lower down the costs. Next challenge is centralized architecture for the PSTN versus distributed networks. And this is really coming across with the second challenge. So again, constantly thinking about where you want to centralize your servers, how you will merge those servers with a distributed network and architecture, and what are the scenarios that you actually want to have traffic goes from distributed networks into your centralized location. In Vonage, we have actually our own 4 dedicated Colocs data centers in the US. We have another one in the UK. But we are heavily users of AWS as well. And the challenge here is to know where to put traffic from our data centers into the cloud and back. The last challenge is something that is related to anyone that is developing mobile application, I think. It's not related to voice over IP. So obviously, we have 2 different types of clients, but we have multiple environments, right? So we have beta environment, we have production, pre-production. We can have multiple environments, and that's actually true for anyone that develop mobile application. And what you eventually want to do is to have one code base for each of your devices, and by performing some kind of a smart logic, and to be able to route your traffic into the relevant environment without the need to recompile the client and changing it, because obviously it's a pain. So just the process you need to go through when you are putting a new client into production environment, or you need to submit it to Apple, you need to wait for the approval. With Google, it's a little bit less pain, but again, you need to take that code, put it in Google Play Store. So you really don't want to do it a lot of times. And the concept here is basically to do it once and having some kind of a mechanism to provision those client properties based on the properties, allowing the client to go into the relevant entry point or the relevant environment. So let's see an example of centralized architecture versus distributed architecture. So here we have 2 users using the mobile application. One is in the UK, the other one is in Singapore. The one in Singapore is using Wi-Fi connection, the one in UK using 3G connection. And we have our data centers in the US. So what will happen typically with voice over IP application is that you're going to have the client register with the proxy over SIP. And then same thing for the other customer. Then if you have the first customer in the UK trying to call the customer in Singapore, then the client will initiate a SIP invite into the proxy. Proxy will send it back to Singapore. The client will ring. When the other client will answer, then we are starting with RTP packets, which is actually the voice traffic. So RTP is the protocol that the voice itself is encapsulated inside those packets. Usually it's over UDP. And then the call will travel from one side of the world all the way to the US and then to Singapore. So again, remember tromboning. So although it is a call between 2 mobile devices, which is what we call on-net call, in that architecture, the traffic will go all the way from UK to the US, from US to Singapore. And obviously, same thing for messages. So the client will deposit messages into the US. The Singapore client will deposit messages also in the US, as well as attachments. Okay, so everything is going from those customers all the way to our centralized data center. And if you think about it, and if you try that with many customers, millions of customers, eventually it will fail. And when I say will fail, is that some of the codes will not be able to connect. Some of the attachments, it just will take too much time for them to upload into our data centers and then the other side to retrieve those attachments. And that's really bad user experience. So one of the things that we are doing is thinking about our distribution network in a way that allows us to basically still keep the registration and the SIP flow going from our mobile clients into our centralized data centers. And that's because of regulations and because of CDR collections and many other reasons. I mean, there's no technical reason not to deploy at the end proxy servers in Amazon Cloud as well. But currently, we are not really doing that. But what we are doing is actually having all the RTP traffic flowing between the relevant clients to AWS instances and keeping the RTP traffic, which is the voice over IP traffic itself, the voice and the packets in the same region. So even though the signaling is going all the way from one part of the world to the other part of the world, and we actually handle that not bad at all because we are using Access SPCs as our front entry points. We can use TCP connections, so we have the ability to retransmit if needed. So that's kind of reliable. With RTP, because it's over UDP, we are putting and offloading that traffic into the relevant zone, into the relevant regions, based on the client location, and allowing the call to flow between zones within Amazon network. So then it's much faster, it's much more reliable, and the call itself, again, if we're doing UK to Singapore, then packets will go from one side to the other, but it's on the same backbone. If it's not the case, and then we have two customers in the UK, and they cannot handle peer-to-peer for some reason, then the call will stay in the same region within AWS as well. For the attachments, we are doing something very similar. We actually deposit the attachments from the clients all the way to S3 in the relevant region. So then we can keep it close to the customer. We don't need to have the clients deposit the attachments all the way to the US if they're not there. But we're still using the centralized point, and we're just having the reference to the S3. Okay, so by doing that, basically we can have control over the messages data structure, and we know exactly for each message if it has attachments or not, and we have all the references to S3 buckets. But in terms of the storage itself, the redundancy, the performance, and the relevant region to be closer to the customer, we just utilizing AWS SDKs from the mobile clients directly to the cloud. So we are using EC2 for our media relays, and let's talk a little bit about that. So we deployed our relays all over. We are using actually all the regions that Amazon can offer, except for Australia right now. And that's really nice. We also using the regions in the US as a backup to our data centers as well. In each region, we are using the multiple zones, and we are using ELB with Elastic IP. So basically, we have the entry point to that region into each zone, and each of our relays is installed with internal IP address. So then, we can have one entry and then distribute it across specific zone and multiple zones within each region. In each zone, we are starting with 4 instances usually, and we can dynamically scale them. Usually not more than 10, although there's no specific reason why we could not do that. But right now, in terms of our performance and needs, we don't need more than that. And the reason is because we are actually using some of the heavy image that Amazon can offer. We really need the intensive CPU usage, so we are using the extra large instance in each of those zones. We don't really need the storage. Relay, the media relay is actually just transferring packets from one side to the other. All the logging we are writing into the local instance storage, but then we actually take them off-site to our centralized site, which is connected through using VPC. So we don't really need the storage. We just use the CPU, some of the memory, and the fact that we have multiple regions to play with and different zones. For all of that architecture, we are using the CloudWatch monitoring capabilities that it is just there. Hook it up into our NOC dashboard so we have real-time alerts, and we can then shuffle traffic between one region to the other as needed. And as I mentioned before, everything is connected back into our 4 data centers in the US using VPC. We implemented ACLs and encryption on top of that. So everything is secured, it's reliable, and by doing that, we can actually offload some of the traffic to the cloud while using still our centralized locations. So I talked about closer to the customer, and I want to describe that process a little bit. So how exactly that algorithm works, how do we figure out where is the customer, what do we need to do with the traffic, to which zone we need to send the traffic. So first, the client sends the SIP registration message to our proxy. And when our proxy gets the message, it actually needs to determine what is the IP address of the client. And in some cases, we need to use standard protocol. Standard protocol is the ability for the client to go to some kind of a mirror and then ask the server, how do I look to you? So when a client is actually located behind net or double net, then the IP address that the proxy will see is the internal IP address, which obviously is not what we are looking for. So therefore, the client will first go into a standard server, retrieve the real IP address, and will send that to the proxy with the internal IP address as well. By doing so, then the proxy has all the knowledge on that specific registration event coming from the mobile client. And by doing a geolocation lookup for that IP address, then the proxy can actually know where that client is located. We implemented the table inside our proxy that based on the geolocation, then we can determine to which ELB entry point the RTP should flow. So in the SDP, we actually determined that. We are using geolocation APIs, and I'm going to talk about it a little bit later, but in a different way. As for the signaling, we are still, as I showed before, we are still using our centralized data centers, but the media actually is flowing directly to the AWS instances. What we are actually experimenting right now is something a little bit different. And that is using Route 53 in order to determine not just the geolocation, but the best routing capability, okay? And from what we saw, in some cases, geolocation will not be that accurate in terms of latency. And it is really, really dependent on the mobile provider as well. So, for instance, some of the mobile providers that offers 3G or 4G services will route their traffic in a different way. Sometimes due to issues on the internet traffic, you know, changes in BGP routing and all of that, it will actually make more sense to route the traffic based on the shortest latency, and Route 53 can do that, all of that behind the scenes. So basically what we are doing is we are thinking about registering subdomains into Route 53, let the client basically go and make that API query directly to Route 53, getting the relevant DNS entry, and then the DNS entry will actually be mapped to the ELB on the right zone, and getting the RTP packets all the way there using our relays. So we started experimenting that. Looks very promising. So that's another method that we are going to take. And obviously, the last thing is an override table. So at the end, we already know that some regions need to go into specific instances. So we can override that. Also, in terms of failures, in terms of disasters, we can just override the table, and from that moment, all the traffic will flow back into our data centers in the US. So we have that contingency in place as well. That's just a small sample of code coming from the proxy. That's a C++, not related to AWS, just showing some of the concepts that I talked about. For the geolocation, we are using MaxMind. And MaxMind, we think it's really nice API. It's basically free for us because we are running the geolocation queries for commercial use. You do need to pay. What they offer a REST API. They also offer data files that you can sync back. And because we are doing the geolocation for every call and for every registration, we really need those performance. So what we are doing is actually syncing those data files on a daily basis to our proxies, and then we load them in memory, and we are doing the API calls within the proxy itself. So by mapping those data files into memory, we can have really, really fast transactions. Again, if you're a small company or you don't want to do that for any of your requests, then you can obviously use their REST API as well, and it works perfectly fine. But if you do really think that performance is something that you need to deal with, and you really, really need to do those geolocation queries really, really frequent, I suggest you to just sync the data file, load them into memory, and then do internal calls. So let's talk about S3 and what we are doing there. So with our mobile messaging API, which is all REST Java, we are using the S3 instance in multiple regions in the US. We are thinking about spreading them all around the world as well. We are always using them in full redundancy mode. So there is a parameter that you actually need to set up for S3 instance to be fully redundant. It costs a little bit more, but it will save you because basically under the hood, AWS will take care to replicate the data. So if there is a failure in one zone or specifically a hardware failure, it will be available for you. If you didn't check that box or didn't enable that flag in the API, it will not happen for you. So you can have downtime. So we are using that. And we are storing our messages, as I mentioned before, in Redis NoSQL structure. That's in our internal data centers for all kinds of legal reasons and regulations. Again, it doesn't mean that you cannot have a Redis instance in AWS. We are just not using that. But what we are doing is that we are rendering a unique ID per message, and we are sending the attachments to the relevant bucket, and then sending, using our internal Java API, the reference ID back to our Redis data structure. So in Redis we have, so Redis is a key value pair structure. We are using it with the hash capabilities. So our primary key there is the mobile number, and then we have all the messages, properties, and attachment references per mobile device in there. So then we can reference back from the client if the client needs to get and retrieve the attachment back from the relevant S3 bucket. That's a piece of code example, again, for our mobile messaging. So you can see we are using the getFile metadata method in order to put the relevant attachment based on the file. And another thing that we are using is we are encrypting each of the attachments. Now, S3 allows you to do two things related to encryption and security. It allows you to actually manage your own encryption, do whatever you want. It's up to you if you want to encrypt the file, but then you are the one responsible to manage the keys, the algorithms. You can do it with PKI, you can do it symmetrically, you can do whatever you want. They don't really care, and then you can just store the attachment there. But it's really heavy and a lot of overload. Also, when you do that on the client, you need to spend some CPU cycles, and that can affect battery life. So what we are doing, and this is a great feature that S3 offers, is just calling their server-side encryption method, and that's it. They will take care for everything for you. So using your AWS encryption keys, you can just call that method, and then while you store the attachment, then you call that method, and it will be stored encrypted into your bucket. Another great feature is that when you retrieve the message, you don't need to take care for decryption as well. So once you retrieve it, if you have the relevant AWS credentials and key, then that's it. It's done. So you can take off all the decryption cycles from the client and just calling that method. Last thing that I want to talk about is the client properties challenge. And again, this is something that is not really related to voice over IP. It is related to multiple environments with multiple clients and how you manage different environments. So this is something that we thought about. And if you think about it, let's say that you have your QA environment, and assuming that your QA environment or pre-production environment is not on the cloud. So you have to manage different IP addresses. You need to manage different properties based on your environment. And you don't really want to compile every time and to prepare and to package that mobile client for that environment. So eventually you want to be in a situation that you have your code base, and then by providing related tags using your source control engine, you just, while you compile it, then you create the relevant client. But there's another issue, and that issue is related to how do you specify what are the IP addresses, right? Because the mobile client doesn't know exactly what is the DNS entries and what other parameters it needs to receive. So that's why we thought about a concept of creating like an entry point that is not related to any of the environments, and that can be in the cloud, and that's always available, and that's very simple. And for that, we're actually using SimpleDB. And for those of you who are not familiar with Simple, actually it is, I think it's the small brother or the first brother of Dynamo. Dynamo is just really, really robust. We don't need that. It's kind of an overkill for what we are doing. So I'm not saying that you cannot implement the same concept with Dynamo. It's just you don't really need to. So SimpleDB is really like an Excel spreadsheet if you think about it. And if you can think about the Excel spreadsheet, we have columns and we have rows. So the rows are treated in Simple as items, and the columns are treated as attributes, and the data itself is the value that is actually like a cell in Excel spreadsheet. So then you have a really simple data structure, and each of the worksheets in Excel is mapped to Simple as a domain. So we came with this concept of domain zero. What is domain zero? Is like the father of all domains. So basically, the client can always go and check with domain zero based on some of the properties that the client knows while we compile it, which is the relevant domain to retrieve the relevant properties out of that, right? So, for instance, I'm a client, I'm a mobile client, and I know my ISO country code, so I know if I'm a client that is trying to connect from the US or trying to connect from the UK, and based on the client tag, I know if I'm a beta client or if I'm a production client or QA client or any other environment. And then, based on that, Simple will retrieve back, based on those informations, what are the relevant, or what is the relevant domain to go and fetch the other properties. So all the server IP addresses, all the other properties that the client needs to know in order to establish all the other sessions. And obviously, if we don't have the client tags, so we can have a default domain which overrides all the rest. And just to give an example, production domain. So production domain can have many, many attributes. Can have attribute 1, 2, up to n attributes, basically. And based on the attributes, in each attribute, it has the relevant data as the property. So then the client can say, OK, give me from production domain all the relevant properties for me because I am iPhone. So do a select query where client type equals iPhone. And then the client will retrieve all the relevant properties for iPhone, all the server IP addresses, all the other flags that it needs to get, all the entry points for the DNS names, for if you have any CMS management systems to render user screens, and all the other parameters. So that's really, really powerful. And as you can see, it's really simple. So one of the, that's an example reaching into domain zero and basically retrieve all the parameters, which you can remember that those parameters will have the other domains. So beta domain, production domain, pre-production domain. And then actually the second query will be very, very likely to that query. But then the select asterisk from will be domain production or domain beta. And then all the parameters will be able to be received into the client. I think that one of the main advantage of using simple is, first, the cost structure is really ridiculous. I mean, it's really, really cheap. You have the same benefits of multiple regions and multiple domains. Although simple has a restriction in terms of your data size. If I remember correctly, they have a restriction of up to 10 gigs. It's tons. I mean, we're never going to use that only for the implementation that we are talking about. And I think the best or the critical thing about simple is that it allows your developers to still run their select queries like it is a regular SQL, although it is not. It is totally a NoSQL structure. It's super fast. They have the SDK support for Android and iPhone. So it's really, really easy to implement and still stay within that SQL zone, which many developers are more familiar with. And then the structure is very similar to that as well. So that's about simple and our implementation to different client properties with different environments. I think that you can take some of the concepts related to that into your own environments, and if you need to manage multiple client versions with multiple environments which are not running in the cloud, then this can be a solution to your need. So with that, I actually want to summarize. So we talk about our implementation of media relays in different regions. We talked about the geolocation algorithms that we are using, the beta that we are starting with Route 53. And Route 53 is really, really powerful solution. So if you're not using that, I really encourage you to do that. It has lots of other features than latency retrievals and just hosting your DNS. So it's really powerful. And then we talked a little bit about S3 buckets and how do we use them with references to the relevant attachments, storing those references in our NoSQL Redis implementation inside our data centers. And then I finish with something that we think that makes sense to do with simple, going all the way from the clients, retrieving the relevant client properties for the other steps, and implementing this domain zero concept, this father domain that actually can retrieve back all the relevant parameters for your mobile clients to go and fetch later on from your different environments. And with that, I actually concluded. If you haven't tried our mobile application, I encourage you to do that. And if you want to reach us, it's you have the Twitters, and that's it. So thank you. I'll take questions later on after we conclude here. So thank you.